All right, guys, this is a review video for physics, talking about something about the parabolic flights that I think a lot of people are confused on. And then we're also going to review the impulse momentum theorem, the idea of momentum, and do chapter 9, number 5 as well, in case you have any issues with that. Okay. All right, so let's go ahead and start with the parabolic flight. All right, I've got this queued up pretty much where I want it.
Was the pilots telling each other the degrees that the plane was flying along its trajectory. And this was a training flight for pilots, which I know how that sounds.
All right.
It just means
So first off, if you look out the plane and you see that, you would be very, very concerned. But obviously they're trying to do that. They're climbing very steeply right here, okay? And at some point as they are climbing, they're going to be moving up and slowing down. So if we're moving up and slowing down, our acceleration points down. If you think back to our elevator problems and our apparent weight, and the idea of these flights is that if you make that acceleration downward, okay, it doesn't matter which way you're moving, if you make that acceleration downward at 9.8 meters per second squared, it'll be approximately, the same thing as free fall. Okay, so this is like the roller coaster ride where you're moving up that first big hill after they let you go, you're moving up and slowing down, you feel like you're gonna float away. If you can maintain that, okay, by moving up and slowing down for a while, and then you crest the hill, and then you move down, speeding up. So moving down, speeding up, the acceleration still points down. If you can make that a nice, consistent 9.8, it's the same thing as being in free fall for an extended period of time. Okay, because that's the only, at that point you're in the plane, and the only, if you're just floating around there, right, the only thing affecting you is gravity. Okay, now normally you can't do that for an extended period of time unless you're up in orbit. Or you have a big plane that has some, powerful engines that allow you to not have to worry about that outside air resistance on the plane. But inside the plane, the air inside the plane, the people inside the plane, the objects they bring with them, they're all in free fall. Even though they're in this plane moving up, slowing down, okay, the only thing affecting them at those moments when they're floating around is the acceleration due to gravity. So it's about maintaining that from their perspective inside the plane. Okay. All right, so let's go ahead and dance.
the pilots are making sure they're flying these types of zero-G flights often enough. They were awesome pilots. Plus, it meant that there were only 4 of us instead of 10 with so much space.
All right, so at this point, they could be moving up, okay, in the plane, but slowing down, okay? This is similar to if I toss something, right? The entire time that was in the air, if I neglect air resistance, it was in free fall, right? The entire time that thing was in the air, it was in free fall. That's what we're trying to get, is that the only thing affecting them is gravity, okay? So to do that, you got to take this plane with all the air inside the plane and make sure that it's in free fall with them, right? Because otherwise, if I did this and I didn't catch it, right, and it was falling and falling, eventually this thing would get going so fast that air resistance would be very, very significant, and then you're not in free fall anymore, okay? So it's not that there's any balancing out inside the plane or anything like that, or that they have zero acceleration. The acceleration of her right now is approximately 9.8 meters per second squared pointed down, okay, regardless of where they're at in their parabolic path, as long as she's floating around.
And there was a dancer on our flight and a startup testing VR goggles, which I got to try. There's so much to tell you! And I wasn't telling you a whole lot of words during the flight. Oh my god! Oh my god! Oh my god! At the same rate, either go up, slowing down, or dive down toward the earth, accelerating at the same rate gravity would accelerate your body if you were falling with no air resistance.
All right, and that's the key.
And guess how long it would take you to fall from cruising altitude at 37,000 feet to surface of the earth while feeling weightless the whole time?
While feeling weightless. So in other words, no air resistance.
And with no air resistance, 48 seconds.
All right, that's just y minus y naught equals v naught t plus 1/2 at squared. She was assuming you were dropped from that many feet. It would take you then
that's it. So as a safer
that long to get to the ground. Okay, so obviously at some point the plane can't keep going down faster and faster and faster because it would hit the ground, right? So they do over and over and over.
These planes go up for 11 seconds slowing down, and then down for 11 seconds speeding up.
And somewhere from like here to here, it's a really good approximation that you are in free fall the whole time. It's like at the top of this toss, right? The pen is moving up and slowing down and then moving down and speeding up. There's a spot in there for this plane ride where you are in free fall. But then obviously it has to shallow out. So it has to start moving down, but not speeding up anymore, right? And at some point here initially, it's not moving up, slowing down, it's moving up, speeding up. So those are the spots where you're gonna feel stuck to your seat if it was like a roller coaster ride.
So you're weightless for 22 seconds each parabola.
It's the same phenomenon as going over the top of a roller coaster, but perfectly timed and balanced to match gravitational acceleration.
But then they repeat that over and over and over for about 5 minutes of microgravity over the whole flight. We did 14 0G or microgravity.
All right. So now if you're not okay with this idea as like where it's the top of the pen flight here, where like moving up, slowing down, moving down, speeding up, if you're not comfortable with that idea that it's like the pen being tossed up in the air, except the plane allows us to maintain that for a lot longer because it can fight against the outside air resistance. Let me know, because I can also do this with more of a visual approach or even numbers. Okay, I can make a little 10-minute video that will attack it from a couple other ways if it's not clicking yet. Now, the big connection that there's parabolic flights weren't just for this, it's also for things in orbit, okay? So for things in orbit, remember the idea is that we are constantly in free fall. Now, up there where the space station is, acceleration of your gravity is like 8.6 meters per second squared because you're a little bit further away from the center of the Earth, but it's still significant. And that acceleration is what allows it to go around the Earth, right? That pull of gravity is what allows it to circle the Earth. We had the previous video on that. If anybody's not clear on that, let me know as well. But they are continually in free fall. When someone says microgravity or 0G, they're talking about, hey, it's the same as if there wasn't any gravity. But if we're talking about near the Earth, okay, you are not somewhere extremely far away where humans have never been before. There's going to be a significant acceleration due to gravity from the Earth on you. Okay, and if that's the only thing that's exerting a force and causing acceleration on you, then you're going to float around. Okay, then you're going to float around. All right, so that was the review of that. Now let's go to OneNote here. Okay, so what I'm going to do is I'm going to show you a couple things you can do that might help with your workflow at home as well. Okay, you're more than welcome to use OneNote to do your work. But obviously I'll take pictures of handwritten stuff or whatever as well. But just in case, because I know some of you did like to use physical books a lot, if you don't like going back and forth on your laptop, I completely understand. So what you could do, whoops, I didn't mean to fold that back yet. What you could do is make a new OneNote file, open up, let's see here, open up the classwork. So here's the classwork, and I've zoomed in. So remember, if you're trying to zoom, don't do the pinch to zoom on the PDFs. Use the little plus thing down here. So I'm going to go ahead and zoom in. Also, if it's ever still blurry, you can always just download it. And now I'm going to go ahead and launch. Oh, maybe I'm not. Oh, there we go. So now I'm going to go ahead. I hit the Windows key, and I'm going to type snipping tool. So their snipping tool pops up. And it's really tiny because I'm putting this on the big screen here, but there'll be in the upper left-hand corner of this thing, you can click New. And then I'm going to highlight the problem. And then I can just, I think it automatically copies it, but just in case it does, I'm going to go ahead and hit Edit Copy because I can't remember. Now I'm going to go ahead and go over to my OneNote, and I can paste it in. All right, and then there's my problem if I don't want to have to go back and forth if you're working on a small screen. I don't know what your workspace is like. I don't know if you got another monitor hooked up or if you're working on paper with the screen here. But if you're trying to do it on a little tiny screen, this might be beneficial in terms of being able to see the problem and your work at the same time. Okay? Now, this one, we also need stuff from example problem 1. So I'm going to go ahead and go back and get some info from example problem 1. Let me zoom out here. My computer is going to be a little sluggish. All right, there we go. And then, oh, it's not letting me do that. Oh, well. Let me do something you shouldn't do. I'm going to go ahead and zoom in. Nope. This computer has a hard time driving the resolution that was on here. Oh, and then it's just gonna, well, I could download this and do it. I'm gonna go ahead and just get the two numbers here. So the, what's going on? Maybe I will download it. All right, so I'll go ahead and show you how to do that since it's being funky. All right, so go ahead and left click download. Download anyway. And then I'm gonna click on this. Oh, it's a JPEG, that's why. And then typically it'll be a PDF and you open it up as a PDF. But there we go. I'm gonna go ahead and get a snipping tool for that after I do a little zoom. And here it would be actually okay to pinch to zoom if it'll allow me. My screen's not responsive. Oh, there we go. There's a big lag. All right. And now go ahead and launch snipping tool again. It's already open, but I'll just do it that way. And I'll do file, I'll do new. And I'll go ahead and get, I just need the beginning of that right there. I just need how fast it's, whoops. Nope, try that again. Click new. Go ahead and get, I'll just get the whole, whoops. I'll get the whole thing. I don't need the whole thing. And then edit copy, switch back over to OneNote. And I put that in here, Control V or edit paste. Okay, so there we go. So I got the numbers from the example problem 1 that was on the left side of, I guess it wasn't a PDF, it was a JPEG. And now we can go ahead and do this problem. Okay? But before we do that, I want to do a little review of some of the ideas. So I'm just going to scroll down here a little bit. We'll go back and do the problem. Just put this line here, so this will be the review. Review some of the big ideas here. All right, pull this back now. All right, so the first one, let's start with the most basic thing here, is that momentum is a vector. So I'm just going to emphasize that by putting a little half arrow, and it is equal to the mass of the object times the object's velocity, which is also a vector. And it'll have units of kilograms times meters per second. That'll be our base units for momentum. There's no abbreviation for that, okay? So what does this have to do with? Well, if I have a mass, if I run that way, I can then define my momentum, okay? It's a certain amount of kilograms times a meter per second, that way. If I'm just sitting here, my momentum, assuming I'm sitting perfectly still, my momentum is 0. All right, so there's the idea of momentum. It has to do with the mass times the velocity of the object. That's it, okay? It's going to point the same way as whatever the velocity was pointing, except it'll be bigger, okay? In terms of it being a vector, it'll be a bigger arrow, all right? So that's my basic idea there of momentum, okay? Mass times velocity. Now, the other big thing that we had was the impulse momentum theorem, otherwise known as FADAT, all right? And the idea here is that the average force, right, times the time equals the change in momentum. That's what we will typically be using. You can use it anytime you want. If you just view it as force times delta t equals change in momentum. You can, if it's technically it's the external force. The outside forces times the time equals the change in momentum. But we're going to a lot of times use it during a collision, during a crash, while you're throwing something, while you're catching something. And in those instances, we'll talk about the average force during the collision, or during the throw, or during the catch, or during the explosion. So that's what this is, that average force that we'll experience times the time of that event equals the change in momentum of the object. Okay? All right, so that's how we will typically use it. But a more broader thing, remember, that's just us rewriting F equals ma. So what was F equals ma? The summation of forces equals mass times acceleration, where those were external or outside forces. That would cause an acceleration. Same thing here. An outside force, okay? An outside force can cause a change in momentum. Okay, so just connecting back to that a little bit. All right, and now I'm going to separate something out here because I think this might help some people. If I just talk about the right side of this equation right here, this change in momentum, what does change in momentum equal? Change in anything. If I wrote delta W there, it'd be WF minus W naught. So it'd be momentum F, final momentum, minus initial momentum. And then I can do algebra substitution stuff here whenever I want. So for final momentum, I could put in mv final, like that. For initial, I could put in mv initial. So you can do stuff like that. There really is only one. I mean, there's this new idea that momentum times velocity, mass times velocity equals momentum. But really, this is our new equation, okay? It started from here, we ended up here. That's our new big equation. But you can substitute in however you like to that. I also want to remind you that the left side of this is called the impulse. So let's say I told you the change in momentum was 50 kilograms times a meter per second. Well, if I said the change in momentum is that, you also know the impulse because they are equal. Okay, it's like this thing equals this thing. So if you have the left, you have the right. Or if you have the right, you have the left. Okay? If I asked you to find the average force, like in the seatbelt problem that you did yesterday, then you have to figure out the change in momentum and have the time to be able to figure out the average force. All right, so now let's go ahead with that little bit of review. Let's go ahead and do this problem. Okay, so it says, suppose a 60 kilogram person, and again, just like our old problems, it might help to look at the units and be like, what is that? 60 kilograms, that's a mass. Okay, so that's the mass of the person. And it says the 60 kilogram person was in a vehicle that hit the concrete wall in example problem 1, which is why I brought in this stuff down here. Okay, the velocity of the person equals that of the car before and after the crash, and the velocity changes in 0.2 seconds. So we've got our time right there in 0.2 seconds. And then we need our change in velocity from example problem 1. Okay, so we have our 26 meters per second, and then it says it stops. Okay, and the person in this problem is attached to the car. So since they're attached to the car, they will make sense. They will come to a stop in the same amount of time, pretty much, as that of the car. And they'll certainly be going the same speed as the car at the beginning, or have the same velocity at the beginning and the end as the car. All right. So what I'm going to do, typical stuff for a problem, I'm going to draw a picture. So here's a person in a car. It doesn't have to be a good picture. Okay, cars go on that way. We're going to hit a wall. I'm going to go ahead and call right positive. And let's go ahead and work through this problem. So we're trying to find, for part A, we're trying to find the average force. So I'll go ahead and write my equation that has F average in it. So I'll go ahead and write that. So F average, there's only really one. I mean, there's lots of different algebraic equivalents of it, but I'm going to go ahead and start there because that's typically where people start, okay? The fat up equation. And then we're looking for that F average. Well, I already know time, so that's good. But I haven't found the change in momentum yet, okay? So there's two ways to do this. One, I can just do this stuff over here. I can change this equation to be like mv final minus mv initial, or m times delta v, and plug in there. If you don't like that, okay, you could go find delta p separately. You could use this idea right here, just get that number and then go back to that equation. My preference is to do it all in that one equation, but if you like separating it out, go for it. Okay, that might help you if you're struggling on seeing the math of what's going on here. Okay, all right. So I'm going to go ahead and be like, all right. So what do I know? This is my V initial. Here's my V final. Got my V initial 26, my V final of 0 because it comes to a stop, and I know the mass of the person. I got M right here, and I've got my T right here. So I'm going to go ahead and write my equation in terms of those variables. So I'm just going to do a little bit of expanding this out. So I'll go ahead and write mv final minus mv initial, because that's my, I'll add a little step in here, that's my momentum final minus momentum initial. That helps you see it, great. You don't have to write that. I don't really care how much work you show, as long as for a problem like this, you give me the first line, so I know what equation you're plugging into with variables. Okay? So I'm going to go ahead and plug into this. I could have also factored out an m. I'm just not going to this time, mainly because my V final is 0. Okay, so I'll go ahead and I'm going to go ahead and write this again before I substitute. F average, delta T. Let's go ahead and plug in my numbers. So delta T is 0.2 seconds. So this will be 0.2 seconds. The mass of the person was, I already forgot, 60 kilograms. It's up there, 60 kilograms. So I'll go ahead and write 60 kilograms. And I'm just, if you're multiplying by 0, you don't have to show it. I'm just doing this for clarity in case, because probably if you're watching at this point, you were a little confused on this problem, this part of the video. So M times V final minus M times my V initial, which I think was 26 meters per second. How fast was that car going when it hit the brick wall? Yes, there it is right there, 26 meters per second. There we go, 26 meters per second. Oh, and I said if you're watching this part of the video, you should watch the end of this video no matter who you are. You should watch the whole thing, but shouldn't have said that. I'm thinking if we were in class, I probably would have had some of you opt out if we were going over it, but that's not an option. All right, so now we'll go ahead and just plug this in. So I'll just have 0, and then over here I'll have the negative of 60 times 26. And then I'll divide both sides by 0.2, and it will be a negative. It'll be negative 7,800 newtons. That's my average force during this collision, which is significant. So that's part A. Now part B. This is where everybody should be tuned in for sure. Pay attention again if you got part A figured out. So now it said, oh, I have the question right here. So now it said, some people think they can stop their bodies from lurching forward in a vehicle that is suddenly braking by putting their hands on the dashboard. So throwing out the hands, okay? And then it says, find the mass of an object that has a weight equal to the force you just calculated. Could you lift such a mass? All right, so I'm going to pretend that we have a weight of magnitude 7,800 newtons. That the size of our force of the weight of some object is 7,800 newtons. So what would be the corresponding mass? Okay, so what would I do? I take that 7,800 and I divide by 9.8 because I want to get the mass. So that would be about 796 kilograms. Now, that does not mean a whole lot to you guys. Okay, so I'm going to go ahead and convert that. This was not part of the problem. That is there's the numerical answer. So 796 kilograms would be the equivalent of almost 1,800 pounds. 1,800 pounds. So now let's put that in perspective of Mr. Willard's. So 1,800 divided by, like, let's say I'm 230 right now. I've lost a little weight. So we'll call it 8 Mr. Willard's. And I'm a big guy, okay? 8 Mr. Willard's. That's a weird thing to write. But yeah, 8 Mr. Willard's, okay? So what does that mean, okay? So if you had your hands up and your elbows locked like you would trying to stop yourself from moving forward in a high-speed crash, it'd be like I'd snap my fingers and all of a sudden there'd be 8 me's in a crate above you. Even if you are a world weightlifting champion, okay, you are not going to be able to keep your arms locked like that. You're just going to be, okay? Now you might say, oh, there's people that can lift a whole lot. They do a whole process. They like take it to their knees and then they do this and then they do that. Like there's a whole thing. It doesn't happen in 0.2 seconds. So remember, this is snapping the fingers and all of a sudden you have to go from nothing to supporting 1,800 pounds or 8 knees in a crate above you or like 10 to 15 normal sized people, okay? You're just not going to be able to do it, okay? You're going to break both your arms, okay? So you can't really stop yourself from moving forward in a relatively high speed crash. In fact, let me put that in perspective as well. The 26 meters per second would be 58 miles per hour back here. So this was a 58 mile per hour crash. This is a pretty bad crash. If you're going 58 miles per hour and you come to a stop in 0.2 seconds, it's going to be bad. You certainly can't keep yourself from moving forward in that kind of a crash. Hopefully common sense would tell you that a little bit as well, but that instinct of throwing out your arms is a bad one. Okay, I hoped this review helped a little bit. The problems that you are, actually they're not really problems. The questions that you guys are doing today that are due tomorrow, by the end of tomorrow, they are just some more conceptual questions. If you disagree with the key on the one about the oil tanker and the raindrop, that is perfectly fine. As long as you back up which one you think has more momentum based on just this, momentum equals mass times velocity, you could say the either one could be correct. So just know that there is multiple answers to the one about the oil tanker and the raindrop. The other ones, just, after you're done, check your answers, see if you're in the ballpark of what they have. There's only 3 questions. Really shouldn't take more than about 10 minutes. And typically when I have these like longer videos like this, I'm going to try to keep the actual work you have to do relatively short. But if you do have questions, let me know. That was it. Have a good day.